Hello, this is my Lab 4 report on oscillations. So here's what I'm going to go over today. So as an introduction, the goal of this lab was to compare predicted versus observed motion of a mass attached to a spring. The purpose of this lab was to observe the energy principle. The system was the ball and the spring, and the surroundings were the Earth. And as a quick results preview, we found more similarity in the X position predicted versus observed data than in the Y position data. Additionally, the change in total energy is 0. So here are the physics equations used, or the physics principles used. So we have Newton's second law is F equals ma, and derived from that is the velocity update formula and the position update formula. Additionally, the energy principle was also relevant. So that's the change in energy equals the work of the surroundings plus other energy transfers. So including slash excluding elements from a system can change what types of energies are acting. And below are the types of energies relevant to this experiment. So we have the spring potential energy, which is 1/2 k delta x squared. The gravitational potential energy is mgh, and the translational kinetic energy is 1/2 mv squared. Here's a screenshot from Tracker of the observed data. So we have the ball and the spring going in a vertical circular motion. And then on the right, we have the plots for the x and y positions, both oscillating. And this data, the data in the table was converted to a CSV file for further analysis. So here's the code. So here's the initial position and velocity. We got the position from the x and y at t equals 0 seconds. And then the velocity we derived from the first two data points. So for the x, that was just 0.109 minus 0.06198 over the time step. And we did the same for the y. So here's where we input the equations. So we have S, which is the magnitude of L minus L naught. And then we also have L hat, which is L over the magnitude of L. And L is just the ball position minus the spring position. And then below that, we have the energies involved. We input the equations for each of the energies, K, the potential, the gravitational potential, the spring potential, and the total energy. Next, we have the net force, velocity, position, or velocity update and position update formulas. And then here were the graphs that the model outputted. So we have the energy graph, and then we also have the x position versus time and y position versus time graphs. So to analyze the graphs, when we look at the energy graph, we see that the change in gravitational potential and spring potential are opposite in sign, and they both oscillate. Additionally, we see that the change in K adds to the potential energies to make the total energy 0. It also oscillates, but it has a smaller magnitude than other energies. In the x position graph, we see that the model accurately predicts the x position. However, in the y position graph, the model does not so accurately predict the y position. So some possible errors, so why that might be. Other forces are in play, so for example, the drag force. We may not have considered other energies, for example, thermal energy. And also, we may have been inconsistent when tracking the center of mass in Tracker. To answer the additional questions, is the energy principle satisfied? Yes, the sum of K, gravitational potential, and spring potential equals 0, as shown by the change in total energy line, which is the orange line. So energy is conserved. The next question asks us to estimate the oscillation period from the x position, which we get by subtracting the two peaks, the time steps at the two peaks, as seen in magenta. And we get 1.709 when estimating from the x position. And then when estimating from the y position, we get 1.519. So the difference in periods could be due to drag forces, also an inconsistent center of mass, and that impacts our calculations of K, the spring force, and the spring potential.